Okay, so this week we're gonna go into statistics, and I think there are many things in statistics that are very important. And if we don't have a clear idea about what they are, um, it's very likely that you cannot follow or catch up in the econometrics contents. So for this part, I recommend you to not just look at the slides, but also take some notes. Okay, we have too many knowledge points that we have to mention, and some of them are not very organized. So I highly recommend you to take some notes, especially when I'm emphasize something. I want you to take notes to have a clearer idea about them. But of course, if you find that the things that I emphasize, it's completely clear for you, or you still remember them really well, then that would be great. Okay. Other than that, I highly recommend you to take a notebook, okay, and take some notes. Okay, not just look at the slides, but also take some notes, because the slides is kind of organized in an example way. Okay. So the first few slides is kind of like a brief introduction of this course. So we're gonna skip this part. And I'm gonna start from page 5. Okay, so here it talks about review of probability and statistics. And it starts from an empirical problem. That is class size and educational output. So the policy question here is, what's the effect on test score of reducing class size by 1 student per class? So if you limit the class size, is that going to improve the scores? And it's important to answer this question because we want to know if we should fund uh, schools to hire more teachers. So we must use data to find out, okay? Theoretically, you can say that, yeah, of course, more teachers, it's gonna be beneficial, but we know that all the fundings are limited, okay? We have to argue that this effect is significant enough or important enough that we can convince, let's say, the government to spend more money on hiring teachers. Okay, so we must use data to find that out, okay? And this is the data set that we're gonna use. It's called the California Test Score data set. It contains all the K6 and K8 California school districts. Okay, so we have 420 school districts, okay? If you are American, you probably are familiar with what school districts is. So school districts, I believe, have many schools, okay? And it's called school districts because that's how the local funding comes from, okay? So they have data on 5th grade test scores, and they also have a student-teacher ratio. That is how many students are in the districts and divided by the total number of full-time teachers. So this is an initial look at the data. You should already know how to interpret this table, okay? So for example, this is the average of student-teacher ratio. It is 19.6, and average test score is 652. So this is what we call the center of the data. And then how spread out it is, we use standard deviation, okay? And sometimes we not just look at standard deviation, but we also look at different percentile to have an idea about how spread out each variable is. So for example, the lowest school districts have 17 students per teacher, while the most crowded school districts have almost 22 students per teacher. The best schools, okay, their test scores is 600, almost 80, while the worst school district's average scores is only 630. Okay. That that probably is significant enough, but I don't grow up here, so I don't know if that's a huge significant difference in the K-8, okay, 5th grade, okay. But I guess it is, okay. Well, this table doesn't tell us anything about the relationship between test scores and the STR. Why? Because we don't know if the worst schools would, okay, so we basically don't know what's the relation between two variables, okay? Even though, let's say, if you look at here, you would say, oh, the worst class have only 17 students, and that is a wrong that's a wrong conclusion because they are simply not related. Okay, these two are simply not related. Okay, let me say it again. So 17 students per teacher is not related to 630 because we're talking about different school districts here. They are put in the same place, but they are not the same school districts. Okay. All right. Okay, don't get confused. It's just I don't know the relationship yet. So how to look at the relationship with between two variables? Okay, we need scatter plot. Okay, how scatter plot is the first thing to do when we want to know if there is any relation between two variables. Okay. Okay, so what is scatter plots? It basically it's a bunch of dots. Okay, each dot is a school district. So we have 420 dots here, and x-axis is student teacher ratio, y-axis is test scores. Is there a relation? Maybe a little bit, right? If you want to draw a line, you kind of see that there is a line that is downward sloping, okay? So, but this line is not so obvious. So we called it weakly correlated, okay? Because it's this line is not very obvious. If all the dots are like around the line, okay? If all the dots are very close to the line, then it's strongly correlated. But now we can see that the dots are far away from the line. So we don't say that it's very correlated, it's just weakly correlated, but there is a negative correlation here, okay? I have mentioned that correlation doesn't mean causation, but let's look at this correlation first. So what does negative correlated mean? It means that if I increase student-teacher ratio, okay, which means if each class increase its size, which means that you have less teachers but more students, right? Then test scores is gonna go down, which is getting worse. Okay, so this figure shows that if we drop student-teacher ratio, okay, which means hiring more teacher, then we can improve the test scores, right? That's how you tell the people who are funding you. Okay. We need more thing to do. Okay. We um we need to get the numerical evidence on whether districts with low student teacher ratio have higher test score, but how? So we need to estimate. Okay. Here, before running a regression, let's talk about what are the statistical tools that we can do. Okay, so first we can compare average test scores in districts with low student teacher ratio with those districts that have high student teacher ratio. Okay, this is called estimation. And then second step, we can test the null hypothesis. Okay, if you don't know what I'm talking about, then you probably need to go back and read some statistics materials. Okay, you should probably still remember something like null hypothesis. That the mean test scores in the two types of districts are the same against the alternative hypothesis that they differ. We call this process hypothesis testing. Step 3, estimate an interval for the difference. We call this process calculating confidence interval. So this is an interval for the difference, okay? It's not the interval of some estimate. It's the interval for the difference in the mean test scores, okay? So we want to know the difference test scores between these two type of districts. And we want to know the confidence interval of this difference. If we are certain percent confident that this interval is above or below 0, then we are a certain percent confident that there is a statistically significant difference between these two type of districts in terms of their test scores. Okay, so let's take a look at how they do it, okay? We have a lot of small knowledge points coming up. Oh, I haven't full screened. Okay, this looks much better. Okay, this is the initial data analysis. Okay. I split my 420 school districts into small class size districts and large class size districts. Okay. Take a look here. Small class size, these districts have 238 districts. Okay. Here I want you to take notes. First, lowercase n. What does lowercase n mean? Every time you see lowercase n, it's sample size. Okay. So why is there lowercase n? Because there is uppercase n. Okay. So capitalized N is population size. All right. This is the first thing you need to take notes. All right. So whenever I say lowercase n, I'm talking about sample size. Whenever I say uppercase n, it's population size. Okay. Second thing is this y bar. What does y bar mean? So sometimes I write y bar simply because it's difficult to write a mathematical equation on Zoom. So y bar, which is this y with a bar on the head, we called it sample mean. Okay. How about s square? Okay. Lowercase s square. I think they have a typo here. There you go. It's S is standard deviation. Okay, these things always happen. S is standard deviation, okay? S square is variance, okay? All right, don't be confused. Put it here. What happened? Oh, okay. Okay, so S is standard deviation, okay? Ugh. This one is wrong. Let me convert it. All right. So here we focus on these two. Okay. We focus on this here. What's the average score of large class? it is 650. And what's the average score of small class? It's 657. So what's the difference between them? 7.4, okay? So we always use this delta, which is this triangle. Okay. Okay, take notes. Triangle always means the difference between two groups. Or a triangle always means difference. Okay. All right. So what are we gonna do here? First, we estimate the difference. Okay, this one is easy to do. It's 7.4. Okay. Second step, we need to test the hypothesis that delta equal to 0. Okay, so delta equal to 0, this is called null hypothesis. Okay, null hypothesis, we also use H0 to do it. Okay, and then now if we have null hypothesis, then we have alternative hypothesis. We usually call it H1. Okay. In null hypothesis, we always see an equal sign. Okay. And in the alternative hypothesis, you never see the equal sign. Okay. One more thing. Why are there so many knowledge points here? One more thing. Alternative hypothesis tells you what site test it is. Okay. Oh, there are too many things. Okay, let's do them step by step. Don't worry. Just take notes. Okay. Step 2, test the hypothesis that this delta equals to 0 can be rejected or not. Okay. Step 3, construct a confidence interval for delta. We'll talk about this later. Okay. Okay. There are too many things. Okay. Step 2. Since we're testing the null hypothesis, right? So there is only two conclusions, which is reject or fail to reject H0. Okay, you never have accept H0 or accept H1. Okay, if you reject H0, then H0 is wrong. Okay, if H0 is wrong, then H1 is right. If you fail to reject H0, then H0 is right. If H0 is right, then H1 is wrong. Okay. This should be step 2. All right. We'll talk about confidence interval later. What does equal sign and never see an equal sign mean? I'll explain it later. Okay. All right, so now I'm gonna clear this page and then we'll go to next page. Okay, if you don't understand something, then let's wait. Okay. Next. Oh, okay, estimation. This one is very typical, okay? Estimation should be very easy. It basically just calculate two sample mean and then take the difference of that, right? So delta equals to sample mean of small class size minus sample mean of large class size districts. Okay, this is how you calculate average. You add them all up and then divide by sample size, okay? What is sample size? The lowercase n. Okay, so 7.4 is the difference, okay? So now this part has finished the estimation. Our next question is this difference large enough in a real world sense? Okay, so what does in the real world sense mean? You have to ask the teachers. The 7.4 makes a huge difference between in in this level of students, okay? So for example, 7.4, does that make a difference between a very good student and a bad student? So another way to do it is to think about standard deviation, okay? So here is some way to analyze whether 7.4 is big enough. I don't think these are very technical, so just take a look. Standard deviation across district is 19.1. Difference between the 60th and 75th percentile of test score distribution is 8.2. Okay, so if let's say if you're a student at the 60th percentile, then if I move you from a large class to a small class, you are probably gonna be at the 75th percentile. Okay, but this is not causal. Let me say it again. This is not causal. This is just correlation. Okay, it's just kind of like if I compare students in a small class and a large class, and the difference between them is as big as the difference between two students at the 60th and the 75th percentiles. So I would say it's relatively large, okay? And so the conclusion here is kind of like subjectively, I think it's large. And so it's big enough difference to be important for school reform discussions for parents and for school committee. Okay, so this is an open question, okay? If it's open, then it means I won't test it. It's just how you interpret estimation results, okay? Because every time you calculated something, you have to interpret it. Is it big enough to make a real world sense? Okay, so real world sense, you have to combine a lot of information to tell. Okay, it's not saying that 7.4 must have a real world sense. Okay, sometimes 0.01 have a real world sense. We don't know. Okay, all right, estimation is simple. Hypothesis testing is difficult. Okay. Here we calculate a difference in means test. This crazy equation looks scary, but don't worry about it. I provided this equation in your cheat sheet. Okay. I feel like these slides have missed a lot of things. Okay. Let's start from the beginning. What is H0? H0 is Cornell hypothesis. Okay. It's something you need to reject or fail to reject. Okay. It always has an equal sign. Okay. So it could be equal or larger and equal or smaller or equal. Okay. It always have an equal sign. And then you have alternative hypothesis. You cannot reject or fail to reject H1. Okay, you don't do anything to H1. It always, it never had an equal sign, so no equal sign. It can be smaller or larger or does not equal to. Okay, this one I have to draw. Or not equal. Okay, so if H0 is equal, then H1 is not equal. Okay. If H0 is, let's say, larger and equal, then H1 is smaller. Okay. So it's always the opposite of each other. H0 and H1 is always the opposite. Okay. And I also said that H1 decides what kind of test it is. Okay. What does that mean? So for example, this pink one, it is smaller, right? So if it's smaller, then we call it less left tail test or left-sided test. Okay. If it's larger, then it's right-sided test. Okay, how about the blue one? The blue one is unequal. Okay, so unequal means that it's two-sided test. Okay, it means it's two-sided test. Okay, so in this class, we are mainly talking about two-sided test. Okay, in this class, we're mainly talking about two-sided tests. We may occasionally have to talk about one-sided tests, but we are mainly talking about two-sided tests. And you should figure out two-sided tests first and then you can talk about one-sided tests. Okay. Let me think. Okay. Yep. Okay, so what is the null hypothesis here? The null hypothesis here is delta. What is delta? Delta is the triangle. Okay. It's just I can't draw. So then I would say delta. Okay. Because this is a two-sided test and we start from two-sided test. Okay. So in null hypothesis, we always have an equal sign. So it equals to 0. Okay, so this is the null hypothesis in this question. All right. Okay. How do you test the hypothesis? Hypothesis testing. Step 1, calculate T statistic. We call it T statistic. Sometimes it's also called T score because it's relatively similar to Z score. Step 2, we calculate p-value. And then step 3, we reject H0 or fail to reject H0. Okay, step 3 is easy. Okay, reject if P is small or T is large. Okay, so T statistics can be positive or negative. So we'll change this into large absolute value of T. Okay. All right, take notes. If you feel very clear about everything, you don't need to. But if you are confused, you should take notes. Okay, lots of things. Let me think about where to start from. So far, we talked about hypothesis testing and all the details about it. We talk about what is H0, what is H1. We talked about what is the null hypothesis of this specific question. So now we have to go from step to step. Okay, step 1. Step 1, calculate T statistics. Okay. It is this thing. So I said that this equation is already in the cheat sheet that I provided you. But I just want to say that this equation is the T equation or T formula for two sample tests. Okay. Why do we have two sample here? because we have a sample that is large and then we have a sample that is small. Okay, we have a large school district and then we have small school districts. So this specific formula for t-statistic is the formula for two sample test. In one sample test, oh, this drives me crazy. Why do they not have a one-sided test, a one sample test? Okay. In one sample test, t-statistic equals to this equation. You should take notes as well. In a one sample test, t equals to this is sample mean, equals to mu 0 divided by SE of sample mean. How do you calculate SE? It's usually delta y hat. We call it delta y hat minus mu 0. Delta y hat, sorry, it's not delta y hat, sigma y hat. Okay, so this thing, we'll talk about it later, okay? Give me some time. One sample test, we'll talk about it later because I think it would be better if we look at the cheat sheet to talk about it. Let's figure out two sample tests first. Although I think if you're feeling confused, then probably you want to pause here and take a look at the materials for one sample test. So step 1, calculate t-statistic of two sample tests. You need to put into the numbers here. Okay, so here there is a lowercase s. Okay. Lowercase s, what it is? It is standard deviation. Okay. Okay. All right. How about lowercase n, sample size? Okay. So you have to put into the numbers into here. And that would be next page. Okay. All right, so I'm gonna clear this page and then let's move on to the next page. So this is the equation that we just saw in the last page. If you put into all the numbers, then you will get t-statistics, which is 4.05. I remember I just said that if t-statistics absolute value is large enough, then we can reject. Okay, remember what are the criteria for rejecting null hypothesis? A large absolute value of t or a small p-value. Okay, how large, how small? So for 5% significant level, your t-statistics absolute value has to be larger than 1.96. So if it's larger than 1.96, then we reject. Okay. We reject the null hypothesis, then null hypothesis is wrong. If null hypothesis is wrong, then alternative hypothesis is right. Okay. So then we can conclude that, oops. So then we can conclude, oh, this is already confidence interval. Okay, so then we can conclude that delta, which is the triangle, is significantly different from 0. Okay, That means the difference between small class and large class, the scores between them are statistically significant. Okay. At what level? At 5% significance level. Where is the p-value go? Okay. Usually you're also required to calculate a p-value. Okay. So the formula for two-sided tests is the formula for two-sided test is 2 times phi minus absolute value of t. Okay, so in this case, what it is 2 times phi minus 4.05. Okay, I already teach you what phi is in the last class. It is the CDF of the standard normal distribution. Okay, so this is standard normal. This is minus 4.05. And this tail area, the size of this tail is phi minus 4.05. So you're going to find this on Z table or use an Excel formula. And then once you get that number, you have to times 2. So then you get p-value. If p-value is smaller than 5%, then you reject the null hypothesis. Okay. P-value approach and t-statistic approach both give you the same conclusion. Okay, that is rejecting null hypothesis in this specific case. Okay, this formula is important. You need to know. Oops. Okay. Okay. So far, everyone seems confused. Okay. If you're confused, then if you're confused, that's fine. That's actually fine because we'll go through exercise together. Okay. But now what you need to do is take down all of these formulas that I asked you to do. I asked you to write down. Okay. So that when we go through exercise, it's very easy for you to look at. All right. Okay, number 3, confidence interval. So this is the formula for confidence interval in a 2 sample test. Okay. This first part is basically delta. This is the standard error that we calculated before. Okay, and now you get a interval which is from 3.8 to 11. So how do you interpret this? You will say that I'm 95% confident that the delta is between 3.8 and 11. Okay, why are you not 100% confident? Because you're only interpreting the data from a sample. You're not getting data from population. Okay. All right. Okay. So another knowledge point. Okay. If 95% confidence interval, which I use CI, okay, is okay, or does not include 0, then the corresponding test, two-sided test, can be rejected at 5%. Okay, what does this mean? This is an axis, right? And then this is your 95% confidence interval. If 0 is here, then you reject. Okay. If 0 is inside, then you fail to reject. Then you fail to reject. Okay. All right. Is that clear? So how about this specific case? So 3.8 to 11 does not include 0, right? So it should belong to this case. Okay. 0 is not included in this confidence interval. So 0 will be rejected at 5% level. Okay. So you should also pay attention to this. Okay. We can also change this into some other number. Okay. We can change that into 99% confidence interval. If it's 99% confidence interval, then this one you change it into 1% significance level, right? Because it's a mirror. P value or and T statistic, or you can say that confidence interval and significance level are two things at two sides of the mirror. Okay. All right. Or you can also have 90% confidence interval and 10% significance level. Okay. They're the same. Okay, so you will see multiple choice questions here. Okay. All right. I spent a lot of efforts in these 3 pages, but they're really important. Okay. And even if you feel confused right now, we'll go through all of these again and again in the exercise. Okay. So let's move forward. What comes next? The mechanisms of the mechanics of estimation, hypothesis testing, and confidence interval should be familiar to you. These concepts extend directly to regression and its variance. So we're gonna learn how to run regressions there. But before turning to regression, however, we'll review some of the underlying theory of the estimation, hypothesis testing, and confidence interval. All right, let's do all the review. Okay. Sometimes I would emphasize, and then you can take notes. First, it's a probability framework for statistical inference. So we have population, random variable, and distribution. We have moments of a distribution, which contains mean, variance, standard deviation, covariance, and correlation. We have conditional distribution and conditional means. And we also have distribution of a sample of data drawn randomly from a population. Okay, so we talk about them one by one. If we have population, then we have sample. Okay. This looks ugly. If we have population, then we have sample. We think of population as infinitely large, even though in the real case, we sometimes have population data. For example, census. Census is a data about the whole population. But in the statistical case, why do we need statistics? Because we can't gather the data of the whole population in most of the times. So we need statistics. What are the data that we can get? That's the sample. Okay. We randomly draw some people from the population, and then the data is sample. We have random variable y. That is, if I randomly draw someone and ask them what's their income or what is their height, then that outcome is a random variable, right? Because the person is random. Okay. Next. Next, we have variance. Variance is a So the person is random, and we can imagine that the outcome has a distribution. For example, if it's height, I think it's probably normal. But if it's income, we would say that, oh, it's probably skewed to the right, okay? But there is a population distribution of Y, okay? What are some of the notations for population? We have mean. Here is something you need to remember. Population mean is mu y, okay? Population variance is sigma y square, okay? And population standard deviation is sigma y. All right. So I always say that if we have population, then we have sample. Okay, this is population mean. This is population variance. And this is population standard deviation. If we have populations mean, population variance, and population standard deviation, then we have sample mean. Sample mean, what does it looks like? Sample mean is y bar. Why is my mouse not working well? Okay, it probably needs to be charged. All right, it's charged. Let's see. We normally don't have sample variance, so forget about it. But we have sample standard deviation. Sample standard deviation. What does it looks like? It is the lowercase s. Okay. Sometimes we use lowercase s y. Okay. But whenever I say lowercase s, it is sample standard deviation. Whenever I say sigma y, it is this one. It is the population standard deviation. Okay. Whenever I say mu, it is the population mean. Whenever I say y bar, it is the sample mean. Okay. We normally don't talk about variance anymore. So good for you. Last thing to remember. Okay. If you have population something, you have sample something, and they use different sign, and you are supposed to remember them. Okay. What else? We have population size. I hope you remember what it is. It is uppercase N. Okay. And then we have sample size. It is lowercase n. Okay. Good. All right. So have an idea about all of these things. Okay. Let's continue. Skewness and kurtosis, you are not required to remember these things. Okay. You're not required to remember these things. You only need to know that if skewness is 0, then it's symmetric. If skewness is larger than 0, then it's rightly skewed. Okay, remember we have a multiple choice in the last quiz, no, not last homework, that says what kind of distribution skewness is larger than 0? A rightly skewed distribution, which is, let's say, income distribution. Okay. Skewness and kurtosis both describe the tail. Skewness basically talks about where the tail direction goes and how long is the tail. Kurtosis mainly talks about how fat is the tail. Okay. So we don't need to remember these things. Okay. Just know that there is these two names, that what are they talking about? Okay. All right. Good. Okay, let's go next. Mm-mm. This is moments of population. Oh, this one. Okay, this is just different distributions with different skewness and kurtosis. This page is not very important. Okay, so next. Mm-mm. Random variable joint distribution. What does joint distribution means? It means that you have two variables, then you have joint distribution. In this class, I don't put a lot of importance in this one. Okay, so you don't need to remember this equation. You just need to know correlation and covariance. Okay, forget about these things. Okay, good. Yeah, you need to know correlation. Okay, so what does correlation? What are the things that you need to remember? If correlation equals to 1, then it means it's perfectly positively linearly associated. If it's -1, then it's perfectly negatively correlated. If it's 0, then they have no correlation. Okay. This is the graph, the scatter plot that you need to know. Okay. For example, the first thing is positively strongly correlated. The second one is negatively strongly correlated. The C panel is not related. Okay. How do you know it's not related? Because it's just difficult for you to draw a line over here. Okay. D panel is a weird case that it is not correlated, but if you run a regression, you should choose a nonlinear model. Okay. Because X and Y are nonlinearly related. Okay. They're related, but they're not correlated. Okay. We'll talk about nonlinear model in the second half of our semester. Okay, good. Conditional distribution is not really important, so let's skip this. Okay, let me repeat again. Let's skip this. Okay, pay attention to the part in before this. If we need to talk about conditional distribution, we talk about it in the semester. So skip. Okay, this part, distribution of a sample of data drawing randomly. Okay, this one is important. Okay, I cannot emphasize more about randomly draw from a population because this is a very important assumption that we have. Okay, because if we assume simple random sampling, okay, pay attention to the wording here. Simple random sampling means that every one I draw from the distribution is randomly drawn. Okay, so let's say the first person I draw is random from this population, and the second person is also random. And in this case, we assume that the first person and the second person have no relation at all. Okay, that means drawing the first person will not change the chance that I draw the second person. Okay, in this case, you have to assume that our population is infinite. Okay, so that is called simple random sampling. Sometimes we also call that IID. Okay, IID. Okay, I don't remember what's the name of IID. It's independently identically distributed or something. Okay, we'll come to that later. It's very important that they are random because all of our model depends on this very important assumption. Oh, IID is here. Independently and identically distributed. Okay, I have good memory. Uh, you have to remember this name. It's called IID. It says that they are independent. First, they are independent. Second, they are also identical. They have the same they are within the same population, so they have the same distribution. Okay. Um, and it could be a little bit abstract, but you should just understand that as the first person I draw, its height is gonna be random, and its distribution is gonna be the same distribution as the height distribution of the whole population, because I randomly draw a person from that population, right? How about the second person? Because I randomly draw the second person, it should be independent with the first person at the first step. Okay, the first person and second person, they are independent. Okay, because I randomly draw both of them. Second is that the second person also comes from the same population, so should also has the same distribution as the first person. Okay. So we call this random sampling IID. Okay, independently and identically distributed. Okay, or more generally, under simple random sampling, yi, I equals to 1 to lowercase n, okay, lowercase n because this is a sample, or IID. All right. So this is a very important assumption that we'll mention in the later of the semester. And when I say IID, then your idea is, oh, she's talking about random sampling. Okay. All right. This framework allows rigorous statistical inference about moments of population distribution using a sample of data from that population. So why do we need statistics in the first place? Because we have limit. What's our limit? That we can't get the data for the population. We cannot reach everyone in the population. So we need to use a sample to tell something about the population. But the problem is this sample, it just doesn't cover everyone, right? So that's the first place why we need statistics at all. Okay. So let's come to estimation. Okay. Let's start from what are the properties of y bar. First of all, y bar is sample mean. Okay. It is a random variable. Why is it a random variable? Because if I randomly draw a sample, and you can think of that every time I draw a sample, I'm gonna end up drawing a bunch of different people. Okay. So every time I draw a bunch, and the next time I draw another bunch, then you can imagine that these two bunch of people have a different average height or different average income or other outcomes. So their average outcome, which is that sample mean, which is this y bar, is random. Okay. So very important, y bar is a random variable. Okay. Some people just can't understand this one. Okay. Because they will be like, wait, y bar is the average, right? And I calculated average, it's a number. Why is it a random variable? Oh, because every time you draw a sample, you end up with a different sample. So you can think of that as average. It's the same with every time you go outside, the weather is random. Okay, it's the same thing. It's just there are too many steps that you forget that it's actually random. Okay. So if it's random, then you will have a distribution. If it has a distribution, then it has a name, and that name is called sampling distribution of y bar. Okay. All right. So if it has a distribution, then we can talk about what this distribution look like. We can talk about what's the mean of this distribution, what's the standard deviation of this distribution. And we can also talk about if this distribution is symmetric, if this distribution is normal. Okay. So that's the next step. This is an example of a Bernoulli random variable. Okay, Bernoulli random variable means that it can only take 0 or 1. Um, the probability of y equals 0 is 0.22. And so probability of y equals to 1 is 0.78. Then we have the expectation of y, which is a weighted average of these two numbers, that is 0.78. We then have an equation to calculate this variable's variance. If you don't remember this is fine, okay? I don't require you to remember this equation. But anyways, its variance is 0.1716. If you take a square, then you can get sigma y, which is standard deviation. Okay, so sampling distribution of y bar depends on the size of the size of the sample. Consider n equals to 2. The sampling distribution of y is, okay, then y bar can have 3 different values, which is a 0, 1/2, and 1. And these 3 are the values of this distribution. So this is a distribution for y bar. Okay, y bar is not y because y can only take value of 0 and 1. Y bar is the average of a sample. Okay. All right. This is one example. Let's assume that your sample size can increase. Okay. This is when the first panel is when n equals to 2. The second panel is when n equals to 5. And you can increase it to 25 and 100. And what happens? Look at the last one. Okay. What does this distribution look like? It looks like a normal distribution. Okay. So then we say that, okay, central limit theorem. I think it's gonna mention later. But central limit theorem basically says that if you have IID and second n is large, then you would come to a conclusion that is y bar is normally distributed. With mean at mu and a standard deviation that equals to something. Okay, I'm gonna talk about it later. Okay, first remember this thing. All right, so what's going on here? This basically says that y bar is going to have a distribution. And if your sample becomes larger and larger, then y bar will belongs to a normal distribution. And this normal distribution has its center exactly at 0.78, okay, which is a population mean, right? Because population mean is 0.78. All right. But it's very narrow, okay? And you can see that this only happens when n is large enough. And you may ask me, oh, when will n be large enough? I would say usually this is a hard to answer question. Okay. It really depends on a lot of different values. But in most of the data analysis case that we have, let's say we have 400 school districts, then we would say that, okay, n is large enough. Okay. We'll discuss this question later. Okay. If you want to be very rigorous, then we have to check a lot of things. All right. So y is binary variable or dummy variable or Bernoulli variable. Y is binary variable. So it's binary distributed, but y bar is normal when two requirements. First, IID. Second, n is large. Okay. So this applies to a lot of things, okay? Y can also be any other shape. Okay. So in this case, y is binary. Okay, it can only equals to 0 or 1. In real case, it can be normal, it can be skewed, it can be uniform. But no matter what, as long as you have IID sampling, as long as your lowercase n is large enough, then y bar is gonna have a normal distribution. Okay. I get that some of you are confused. This is why sometimes in some class, once you finish your final exam, you feel like you can throw it away. But then once you finish statistic class and then you come to econometrics class and then you realize that, oh, I shouldn't forget about all of those things. All right, don't be sad. Let's take a look at the details. Things we want to know. Oops. About the sample. What does the sample mean? The mean of the sample means distribution is 0.75. So then if this holds, then we say that y bar is an unbiased estimator of mu. What is mu? Remember? Sample mean. Sorry. Mu is population mean. Y bar is sample mean. Okay. At the same time, y bar is also called estimator. Okay, take notes. Estimator is a random variable. Okay, in this case, y bar. Okay, estimate is a non-random number. Okay. All right. This will show up in one of your multiple choice. Okay. All right. So what is the variance of y bar? This depends on the n, remember, because if you increase the n, you saw that normal distribution become narrower and narrower. So here is the equation for the variance. Okay. This one you need to know. Okay, expectation of y bar equals to mu y if you have IID and large n. Second, variance of y, okay, y bar equals to this thing. This thing is not, this equation is not required, okay? These are required, okay, IID. This is not required, okay? Because something else is required, which is this one, okay? This is what you need to remember, okay? The rest of it is for your curiosity of knowledge. Okay, so variance of y bar equals to sigma y squared divided by n. What does that mean? It means that if n increases, the variance is gonna drop, right? Because the n is in the denominator. So if sample size increase, variance of y bar is gonna drop. Then that is consistent with the fact that if I increase n from 25 to 100, you see that normal distribution become narrower, right? If it's narrower, then it's less spread out. If it's less spread out, that clearly we can see that variance is dropped. Okay. All right. So here is what you need to remember. Okay. Check if you have take notes. This is also what you need to remember. Y bar is an unbiased estimator because expectation of y bar equals to mu y. Okay. Because that it is unbiased estimator. Second point is not important. Okay. You don't need to remember what inversely proportional. No, you just need to have an idea that, okay, if n increases, which means if I have a larger sample, then it's going to be less spread out. Okay, because the variance of y bar is going to drop. All right. Good. Next. Here we come. Central limit theorem says that if you have IID and if n is large, where does IID go? Okay, you need IID as well, but here you assume IID is there. Then you have the samples length distribution that becomes more and more tightly centered around mu y, and it becomes normal. Okay, this is a little bit messy. Okay, so I'm gonna write down what you need. What you need is, first you need IID. Second, n is large. Okay. All right. And then using central limit theorem, we call it CLT. Using central limit theorem is not an equation, it's a theorem. It's kind of like a theory that from what you need to what you can conclude, what you get, what you know. Okay. What you know is that y bar is normal. okay? Or y bar's distribution is normal, okay? And what is the normal distribution's mean? Its mean is exactly the population mean, okay, which is mu. Okay, it's exactly mu. And its variance, okay, its variance shrinks with larger sample size. Okay. Okay, so next time if you ask me what's central limit theorem, don't expect me giving you an equation, but expect me to give you what this comes, okay? Central limit theorem tells you that if you have random sampling, which we also call IID, if you have large enough sample size, which is the lowercase n, then using central limit theorem, you will know that the sample mean, which is a random variable or an estimator. Okay, I'm trying to stuff a lot of things into your brain. This y bar's distribution will be a normal distribution, okay? And what's the mean of this normal distribution? It's exactly population mean, okay? And how spread out is this normal distribution? Its variance equals to sigma y squared divided by n, and its variance will shrinks with larger n. Okay, probably let's write it down also. Okay, its variance equals to, okay, sigma square divide by n. Okay. All right, this is what you get. Okay. How many more pages are there? I'm getting thirsty. Let's go. Law of natural numbers. Law of natural numbers is not actually that important. Let's skip law of natural numbers, okay? Okay. More about central limit theorem. Oh, this is the another explanation of central limit theorem. Again, you need ID. Second, n is large. Then what are you gonna get? You're gonna get that this is approximately normally distributed with center equals to mu y and variance equals to sigma y squared divided by n. If you standardize this thing, okay, that is, this thing is gonna be standard normally distributed. Okay, that is, the standardized y bar is approximately distributed as n01. And also, the larger the n is, the better is the approximation. Why? Because it's gonna be less spread out. Okay, if it's less spread out, then it's more concentrated at the population mean, okay, which is what we want because we want it to be close to the population mean so that the sample mean I calculated can tell me something about the population, right? Because you want the sample average income equals or close to the population average income. If they're not close, then what's the point? Okay. All right. So the larger n is, the better its approximation. This conclusion is kind of like, oh, I already know it. How do you get it after so many complicated steps? But this is what it needs. It basically says that if I want to know what's the average income of the US population, then 100 people is definitely not enough, right? You have to get 60,000 households. and ask them what's their income, or even more. Right, 60,000 households, it's definitely been more useful than just asking 100 people randomly, right? Why? Because it's more accurate. And that is exactly this conclusion. The larger is n, the better is the approximation. But it's just central limit theorem gets you go through all the difficult abstract things and reach this conclusion. But let's ask, why do we need so many complicated stuff? Because the sample mean is still inaccurate. Okay, it is still not exactly population mean, or you never know. You never know where the population mean is. All you get is just a sample mean. So you also want to know how close is the sample mean to the population mean, right? So you need that sample distribution. Okay, that's why we need statistics. Okay. All right. Okay. This is another example. Okay. Sample and distribution. Okay. Interesting. This is summary. Again, if you have IID and your N is large, then Y bar is, oh, this one is not required. Okay, this one, law of large number not required, but this part is required. Okay, Y bar is normally distributed according to central limit theorem. Okay. All right. Why do we use Y bar to estimate mu Y? Again, because I want to know how much is the average income of the United States. But I can't reach everyone, so I end up reaching 60,000 households. Okay. 60,000 household is a number that the Bureau of Labor Statistics use. Okay. Every month they will reach 60,000 households, but they don't ask income. What I remember is that they ask whether they have a job. Okay. Every month, the Bureau of Labor Statistics published unemployment rate, and that is how you know if the U.S. economy is recovering or not. Okay. What I know is that it's a little bit stagnant right now. The recovery is stagnant. Yeah. So we want to use the employment status of this sample to have an idea about the whole population. Okay, think about that. So first, it has to be unbiased. Okay. Second, we hope that it's consistent. Although I only require you to understand unbiasedness. Okay. We don't need to understand what is consistent so far. Okay. These things are also not required right now. Okay. All you need to know is based on central limit theorem that Y bar is unbiased. That's why we can use the employment status of that sample to have an idea about the whole population. Okay. Okay. Let's talk about hypothesis testing. So I already talked about a lot of the knowledge point about it. This is hypothesis testing, okay? H0 and H1. Remember we said that H0 is always has an equal sign, and then H1 doesn't have an equal sign, okay? Sometimes people will write this in this way. Okay. Sometimes they write it in that way, but in this semester we'll mainly focus on two-sided test. Oh, not this one. We mainly focus on two-sided test. okay, which is the third one. Okay, so what does hypothesis testing actually mean in the first place? Why do we need this number? This number is for us to reject. Okay, we never have accept. This is very important. So why do we need to reject something? If we've managed to reject, that means that we believe that that is not true. Okay, so then I cannot conclude the conclusion of the null hypothesis. So for example, let's say herd immunity, right? How much percent of the people of immunity, how much of the proportion is needed to achieve herd immunity? People don't know it right now. Okay, some model says 60%. So that's usually the number here. Let's say 60%. Okay. So you're testing whether mu y mu equals to 60%. Okay. If you reject, then it means that you have not achieved 60%. Okay. Let's say we're using a two-sided test right now. Okay. If you reject, then you are not at 60%. Then you have not achieved herd immunity yet. So null hypothesis usually use a number that determines your decision. So let's say we have not reached herd immunity, then what does the public officials have to do? Then they have to keep vaccinate people to reach that, right? So null hypothesis is about a number that you want to reject or fail to reject, and that rejection or fail to rejection is going to determine your policy action or your business decision. Okay. All right. So in the previous case, it is 0. So you want to decide whether the difference between two type of districts, they have a significant different test scores. Okay, so that's the logic of hypothesis testing. Okay, although it doesn't come very natural. Okay. Some terminology for testing, you can calculate, I think you first calculate t statistic and then you calculate p-value. Okay. This is another equation for p-value, although I'm not really into this one. Okay. I require you to remember the one with two-sided test. Okay. All right. Again, this is p-value. This one you need to know. Okay, why do we need to times 2? Because we need to calculate a two-sided test. So we are actually getting the area of these two blue area. We times 2 because we know that as long as we get one of them, the other one is symmetric. Okay, so then we can get it. I don't really like this one. This should be 2 times phi minus absolute value of t. This is p-value, okay? And how do we calculate t? T equals to y bar minus mu 0. Mu 0 is the number in your null hypothesis. Divide by standard error of y. Okay. In practice, this thing is unknown. It must be estimated. Okay. So how do we estimate that? Let's continue. Okay. after you take notes, so let's continue to know. Let's continue to figure out how do we calculate that number. Okay, so estimator of the variance. Okay, remember what is estimator? Estimator is a random variable. Okay. These things are not really important. What you need to know is just we can use sample standard deviation or sample variance to approximate population variance. So here is how we're gonna do it. Okay. This is how we're gonna do it. Okay. So what's the number you're gonna put under here? That is lowercase s divided by square root of n. Okay. All right. This one is important. Okay. I don't require you to remember this whole part, but the last one you need to remember. Technically you don't need to remember it in your brain. Technically you can have this formula ready when you're doing the exercise. Okay. So this is how you calculate a t-statistics. All right. Okay. This is not the recommended p-value formula. So don't look at this one. Okay. Too many formulas is gonna make you crazy. So use the one that I gave you for two-sided test. Okay. What's the link between p-value and significance level? If p-value is smaller than significance level, then you reject. Okay, that's very simple. You reject if absolute value of t is large or p-value is small. All right, at this point, you might be wondering what happened to the t-table and degree of freedom. This this thing is not going to show up many times in this semester, but it's very important in the statistics part. That is, when t is not large enough, then its distribution is called t distribution, and it has a degree of freedom. Okay. In this class, what you need to remember is if n is large enough, then t is z. Okay. Okay, remember this. Okay, if t is, lowercase n is large enough. Okay, in this case, larger than 50 is large enough. Okay. Then t is z or is almost z. Okay. If t is almost z, then t-table not needed. Use z-table because much more easy. Okay. Mm-mm. Okay. All right. If we really need to go to look at a t-table in this semester in the exercise, we'll talk about it. But now let's first figure out the common case. Okay. All right. Mhm. Okay. This is summary. Okay. Oh, here it says that if n is larger than 30, t is already very close to z. Okay. I think some textbooks says that it needs to be 50 or more, but 30 or more, it's very easy to reach, right? We have 420 school districts. That's way larger than 50, not to mention 30. Yep. Okay, last part, confidence interval. So I hope you're not asleep yet. We usually calculate 95% confidence interval. Sometimes we calculate 90 or 99%. Okay. Um, these are the equations that you need to remember. I recommend you to remember this one. Okay. And remember that if confidence interval includes 0, then we fail to reject 0. If it doesn't include 0, then we can reject 0, right? So confidence interval and hypothesis testing are two sides of one mirror. Mhm. I really need to know how long does this end. Oh, last 2 pages. Great. Summary for the 2 assumptions. Okay, first is IID. Second is this thing. Okay. This is the 4th moment. What you need to know is just this thing means that you don't have lots of outliers. Okay. Large outliers. Rare. Okay, rare large outliers, let's say. Okay, you don't have a lot of super large outliers to make the distribution crazy. Then once you have large n, you will have the sample distribution of y bar according to central limit theorem. And using central limit theorem, you are able to calculate t statistics, p-value, and confidence interval. Are assumptions 1 and 2 plausible in practice? Yes. Okay. Because most of the cases our sample are randomly drawn, and in most of the cases we don't have a lot of outliers. If there are some rare outliers, then we can just drop it. Okay. So it's practical. And let's go back to the original policy question. Okay. So we're not gonna go back to that right now, okay? This one, we'll talk about it later in the semester when we talk about regressions. Okay. All right, that's it for this. Let me open the cheat sheet. All right, so after I have talked about so many things, it's basically just come down to this 2 page of stuff. Okay, you can find almost all the equations here. If you have more things to deal with, then it will be Z tables. Okay, or you can use Excel. Okay. All right. I'll see you next class to talk about homework and quiz. Okay.